Welcome to the Deep Dive, your shortcut to understanding the fascinating forces shaping our world. Today, we're plunging into a really cutting-edge area of artificial intelligence. It's all about how to best teach those incredibly powerful large language models. The brains behind a lot of the latest AI, how to actually use external tools effectively.
Yeah, things like search engines for up-to-date info or calculators for getting the math right, even code interpreters.
Exactly. Tools to make them more grounded, more capable.
And it feels like this whole AI landscape is just evolving so incredibly fast. For you, our listener, trying to keep up with every twist and turn, well, it can feel like a full-time job, honestly.
That's definitely where we come in. Consider this deep dive your expertly curated guide to one really crucial aspect of this evolution, how we're making these AI models, well, smarter and more connected to reality.
Precisely. And to get there, we're digging into some fascinating work. It's from the University of Illinois Urbana-Champaign, a research paper called ToolRL, Reward is All Tool Learning Needs by Kian and their colleagues.
Okay, so our mission today, we want to break down what it takes to train LLMs for something the researchers call tool-integrated reasoning, or TIR.
Yeah, TIR. We're going to explore how something pretty fundamental, a really well-thought-out reward system within reinforcement learning, or RL, how that can dramatically boost their abilities, and also how well they adapt to new situations.
And I hear there's some genuine surprises about what actually makes a reward useful here.
Oh, definitely. Some counterintuitive stuff. Okay, so let's dive right in. Why is this whole idea, LLMs grabbing and using external tools, why is that becoming so, well, essential now?
Well, what's really interesting is that this tool-integrated reasoning, TIR, it's fundamentally about helping LLMs get past some of their built-in limits. I mean, think about it. Their knowledge is kind of locked in time, right?
Sure.
Based on the data they were trained on, so it gets outdated fast.
Right, and they can trip up on calculations sometimes.
Yeah, or their reasoning can sound super convincing, but maybe lack real depth sometimes.
They can state something totally wrong with such confidence. It's kind of unnerving. But give them access to, say, a search engine. Suddenly, they can pull in the very latest information.
And calculators mean perfect accuracy for math problems.
Exactly. And code interpreters let them handle much more complex logical tasks. So TIR is really about anchoring their reasoning in the now and giving them specific, powerful skills.
So it's not just about spitting out text anymore. It's more active, more functional engagement with the world.
That's a great way to put it. And we're seeing them interact with more than just those three, too.
Oh, yeah. Like what?
Well, things like databases, to fetch specific data points, or APIs to connect to all sorts of online services, even tools that can generate images or music based on prompts.
Wow, okay.
But the key thing is, it's usually not just one step, it's a sequence. The LLM has to figure out, okay, do I need a tool? If yes, which one? Then how do I use it correctly? What do the results mean? And then maybe it needs another tool, or maybe now it can finally give the answer. It's this whole cycle, feedback and action. Very different from just processing text.
It really sounds like we're inching closer to something that can genuinely act in the world, like an agent, almost.
And if you zoom out, look at the bigger picture. That's exactly where this is pointing. TIR is really, you could say, at the heart of this whole emerging concept of LLMs as agents.
LLMs as agents, okay.
Yeah, think about AI assistants that don't just answer questions, but proactively do things for you.
Yeah.
Conduct deep research, speed up scientific discoveries, automate tedious work, maybe even help with complex everyday choices. That's the kind of potential we're talking about unlocking.
Okay, that paints a clear picture. So TIR is obviously super important. How are we currently trying to teach LLMs these tool skills?
Yeah.
And where are the sticking points? The paper mentioned SFT, right? Supervised fine-tuning.
Yes, exactly. Right now, the main method is supervised fine-tuning, or SFT. Essentially, what researchers do is they create these big data sets, lots of examples showing the exact steps for using different tools to solve specific problems.
Okay.
Then they train the LLM by basically just showing it these pre-made how-to guides over and over again.
Ah, so it's like giving the AI the answer key and all the work shown to get there.
Yeah.
What's the catch? Why isn't SFT the final answer?
This is where you start seeing the cracks. SFT can work reasonably well for the exact kinds of problems it was trained on, but it really struggles when it sees something new. If
Oh.
the LLM runs into a tool situation it hasn't explicitly seen before, or maybe the steps needed are just a little bit different, it often just doesn't know how to adapt.
It can't improvise.
Right, and its ability to explore new ways of using tools is super limited. It's mostly just copying what it's already seen.
The paper had that really great analogy, didn't it?
Yeah.
About overthinking, but really just kind of mimicking cues. Can you unpack that a bit?
Oh yeah, that was insightful. Figure 1 in the paper illustrates it really well. Imagine a scenario where maybe using a certain tool isn't actually the best approach for the task. An LLM trained with SFT, especially if it saw examples with lots of complex-looking steps, might still try and force that tool to work. Why?
Because it saw something similar in training.
Exactly, because its training data showed tool use in situations that looked similar on the surface. It might even spit out phrases like, "but wait," in its reasoning, not because it's genuinely reconsidering its approach.
But because that phrase was just in the training example, it's copying.
Precisely. It's more about matching surface patterns than, real understanding and flexible problem solving.
Okay, that makes the limitations really clear.
Right.
So the researchers were basically asking, is there a better, more robust way to teach this than just showing examples? And they landed on reinforcement learning.
That was the central question. Could RL offer a better path? Because reinforcement learning, RL, it's a fundamentally different approach. Instead of showing the model the right answers explicitly.
You let it learn through trial and error.
Exactly. The LLM tries taking actions like using a tool, and then it gets rewards based on how well that action worked out. The goal is for the LLM to figure out a strategy or a policy that gets it the most reward over time.
That sounds like it could be really powerful for developing those agentic tool using capabilities the paper mentioned. But I can already see a challenge. Figuring out the right rewards. That seems tricky for something complex like tool use.
You've absolutely nailed a core difficulty. It's not like, say, solving a simple math problem where there's one clear right answer. With tool use in TIR, it's much more nuanced, right?
Right.
There might be several tools that could work. Each tool might have different settings, different parameters you need to input. So a simple reward that just checks if the final answer is correct, that's often just not enough information for the model.
It doesn't tell the model which steps were good or bad along the way.
Precisely. It doesn't provide that detailed feedback the model needs to learn. Which specific tool choices or parameter settings were actually helpful versus which ones were maybe inefficient or just plain wrong.
So even if the final answer is right, if the LLM took some crazy roundabout route using 5 unnecessary tools, a basic reward wouldn't catch that.
Exactly. That lack of specific feedback makes it really hard for the LLM to learn the subtle art of using tools effectively. And this is really where this research makes its mark. The authors stress that their work is the first comprehensive study on reward design, specifically for tool selection and use within RL for LLMs.
First comprehensive study. Wow, that really underscores how new this focus is. So what did they actually do in this study? How did they approach it?
They were really systematic about it. They looked at a whole bunch of different reward strategies. They broke it down along 4 key dimensions, basically. The type of reward, like what specific behavior are we rewarding? The scale, how big should the reward be? The granularity, how detailed is the feedback? And the temporal dynamics, should the rewards maybe change as the model learns?
Okay, type, scale, granularity, dynamics. Got it.
And based on exploring all that, they came up with their own principled reward design tailored for tool use tasks.
And they didn't just dream this up, right? They tested it.
Oh, absolutely. They used a pretty advanced RL algorithm called Group Relative Policy Optimization, GRPO.
GRPO. Okay.
Yeah, it's apparently quite good for these complex action scenarios, like deciding between different tools. They used GRPO to train LLMs using their new reward system.
And the results, were they good?
Really quite remarkable, actually. Across several different benchmarks designed specifically to test tool use, their approach led to, on average, about a 17% performance boost compared to the base models, the ones with no special training.
Wow, 17%.
And maybe even more impressively, a 15% gain over models trained with that standard SFT method we talked about.
Okay, 15% better than the current standard. That's significant.
It really is. It just highlights how critical getting that reward design right actually is.
All right, now we're getting to the really juicy stuff, the core insights. What did they actually discover about what makes a reward work well for teaching tool use? What were the surprises you hinted at earlier?
Okay, so one of the most, well, counterintuitive findings was about the length of the reasoning process. You'd naturally think, wouldn't you, that if an AI is thinking more, taking more steps, it's probably doing better.
Yeah, seems logical. More steps, deeper thought.
But they found that longer reasoning trace is not inherently better. And get this, actually giving rewards just for the length of the reasoning could sometimes hurt performance.
Really? Hurt performance. That completely goes against intuition. Why would that happen?
Well, their analysis, you can see it in Figure 8 and Table 5 in the paper, suggests that while encouraging more steps might seem like it's promoting deeper thought, it can also lead to unnecessary complexity, maybe even getting tangled up in overthinking things, which at the end of the day makes the tool use less effective, less efficient. It really challenges that common assumption. More steps is better AI reasoning. Not always true, it seems.
So it's about the quality of the steps, not just the sheer number of them. Even for AI using tools, that's a really key point. What else stood out?
Another really important insight was around the idea of dynamic reward scale. They found that having a dynamic reward scale helps models transition smoothly from simple to complex behaviors.
Dynamic scaling. So the rewards change over time. How did they do that?
They looked at two main ways. One was a kind of two-stage approach. The other was a more gradual, fine-grained adjustment.
Okay, what's the difference? Two-stage versus fine-grained.
So the two-stage way was like this. Early on in training, they'd heavily reward the LLM just for getting the basic structure right, using the special tokens like think, tool call, response in the correct sequence.
Right, just following the rules.
Exactly. Then later in the training, they'd abruptly shift the focus, putting much more weight on rewarding the actual correctness of the tool use itself.
Okay, so phase 1, format. Phase 2, correctness. And the fine-grained way.
That involved a much more gradual change. Throughout the entire training process, they slowly adjusted the weight given to format versus correctness.
Like slowly turning up the dial on correctness while maybe slightly turning down the dial on format.
Kind of like that, yeah. A smoother transition.
And which one works better? The abrupt shift or the gradual change?
The results were pretty clear. Figure 10 and Table 6 show this. The more gradual, fine-grained adjustments were more effective. That abrupt shift in the two-stage method wasn't as good. It seems like slowly increasing their emphasis on the harder goal, using tools correctly while still making sure the format was okay, allowed the models to learn more stably, more effectively.
It's like learning anything complex, isn't it? You need to get the basics down before you can smoothly integrate the harder parts. You can't just flip a switch.
Exactly, like learning an instrument, maybe. Master the scales before you tackle the concerto.
That makes perfect sense. Okay, so gradual adjustments win. Now, what about this granularity of reward? That sounds like it could be really impactful.
Oh, absolutely crucial. They found that fine-grained reward decomposition was key for stable and effective learning. So instead of just giving one overall score like, yep, the whole tool use thing was correct, or nope, it was wrong.
They broke it down.
They broke down that correctness reward into much more detailed pieces. Think of it like, instead of just getting a pass-fail on a big exam, you get feedback on each individual question.
I see. So the LLM gets much more specific guidance on what it did right or wrong.
Precisely. So instead of just saying tool use wrong, the reward system could pinpoint why.
What specific bits did they break it down into?
They looked at three main things. Did the LLM choose the right tool name for the task? Did it use the correct parameter names for that chosen tool? And were the values it plugged into those parameters actually accurate?
Okay, tool name, parameter names, parameter values. That's detailed.
Very detailed. And this gives the model much richer feedback compared to just a simple correct and correct signal. Figure 11 and Table 7 in the paper really drive this home. This detailed feedback led to significantly better performance than coarser methods that might just check if the overall tool output matched something.
It's like telling a student doing a math problem, not just, you got it wrong, but look, you made a mistake in step 3 when you carried the 1. That specific feedback is gold for learning.
Exactly that. And based on all these insights, the lengthening, the dynamic scaling, the granularity, the researchers built their specific reward system. Can you walk us through the main components of that?
Sure. So, yeah, their system had two main parts, a format reward and a correctness reward. The format reward was pretty simple. It just checked, did the LLM's output follow the rules? Did it use those special tokens like think, tool call, and response in the right order?
Like structurally sound.
Yeah, exactly. It was a binary. Either the format was right, reward of 1, or it was wrong, reward of 0. Simple.
Okay. And a correctness reward, that's where the granularity came in.
Right. This one was more complex. It could range from -3 up to +3. And it was calculated based on those three subcomponents we just talked about.
Mhm.
First, tool name matching. Did it pick the right tool? Second, parameter name matching. Did it use the right labels for the tool's inputs?
Mm-hmm.
And third, parameter content matching. Were the actual values it provided for those inputs correct?
Okay.
They combined the scores for those three things to get an overall correctness score, and then they just normalized it to fit that -3 to +3 scale.
What seems really smart about that is how they clearly separated things. There's the structural part, did you follow the communication protocol? And then the semantic part, did you actually use the tool correctly and meaningfully?
Yeah, it seems balanced and also interpretable, you know? You can see why it got the reward it did.
Which likely contributed a lot to their success.
Okay, so they developed this really thought-out reward system based on their findings.
Yeah.
How did they actually prove it worked? What kind of tests or experiments did they run?
Right. They didn't just stop at the theory, they put it through its paces rigorously. They used a bunch of different data sets specifically designed to test various aspects of tool use. Names like toolac, hammer, masked, XLAM.
Huh?
These cover a range of scenarios, from just deciding if a tool is needed, all the way to complex situations with multiple tool uses in one go. And they mainly used that GRPO algorithm we mentioned to do the training.
And the bottom line, what did the results show on these benchmarks?
Pretty much across the board, on benchmarks like the Berkeley Function Call, Leaderboard, BFCL, and API Bank, their models, trained with GRPO and their special reward system, consistently did better. Better than the basic untrained models, obviously, but also better than models trained with standard SFT, and even better than models trained using PPO, which is another common RL algorithm.
So, beating the baselines and the standard methods.
Yeah, tables 1 and 2 in the paper lay it all out. They saw like an absolute gain of around 10% over the SFT models on average, which is a really solid improvement in these kinds of tasks.
10% jump is definitely nothing to sneeze at.
No, it's substantial. And here's something else interesting they found. Models trained with GRPO right from the start, a cold start they called it, often performed better than models that were first pre-trained using SFT and then fine-tuned with RL.
Wait, really? Starting from scratch was better than starting with the SFT pre-training. Why would that be?
They speculated a bit about this. They suggested it might be that the initial SFT training could sometimes lead to a kind of overfitting. Like, the model learns the SFT examples too well, and that actually makes it harder for it to benefit fully from the more flexible RL training later on. Figure 5 in the paper touches on this.
Huh. That's fascinating. So sometimes that initial head start from SFT might actually hold the model back a bit later.
Potentially, yeah. It's an interesting wrinkle.
Okay, so they got good scores on the benchmarks. Did they also look at how well the models could, like, generalize,
Yeah.
handle things they weren't explicitly trained for?
They did, and that was another strong point. The GRPO trained models showed really impressive performance in unfamiliar situations. For example, using tools related to programming languages they had never encountered during training.
Wow.
And also tackling new kinds of tasks, like figuring out if a suggested tool was actually irrelevant to the problem, even though detecting irrelevance wasn't a specific training goal.
That ability to adapt and handle novelty?
Yeah.
That feels like a step towards more genuine intelligence, doesn't it?
It really does. Figure 7 and Table 4 highlight these strong generalization abilities.
Okay.
And just one more test they did. They tried it on a question-answering benchmark called Bamboogle QA. Here, the main goal is just getting the final answer, right? Using tools is just a way to get there. It's not the core task itself.
More open-ended, less structured.
Exactly. And Table 3 shows their method achieved high accuracy there, too. And importantly, it did so without making tons of unnecessary tool calls. It seemed to use tools efficiently, strategically.
So the reward system worked well not just for structured tool tasks, but also for these more flexible, real-world-ish scenarios.
Yeah.
That's pretty
It
convincing.
really speaks to the robustness of their approach.
And they also circled back to analyze those reward strategies again, right? To kind of double-check those initial findings.
Yes, they did some further analysis, digging deeper into those 4 dimensions: type, scale, granularity, temporal dynamics. And it basically confirmed their earlier conclusions. They showed again that just rewarding longer reasoning didn't consistently help, and could even hurt performance. That's in Table 5 and Figure 9.
Okay.
They also reinforced the idea that giving more weight to the correctness rewards compared to just the format rewards was really important for getting good generalization. Table 6 shows that.
Right. Correctness matters more than just following the format rules, ultimately.
And finally, Table 7 provided more evidence supporting their big conclusion. Those finer-grained, more detailed reward signals really do lead to better training outcomes overall.
Okay, let's try and wrap this all up for you, our listener. What are the absolute must-know takeaways from this deep dive into rewarding LLMs for tool use?
I think the number one thing is just how incredibly vital, thoughtful, well-designed reward systems are for getting LLMs to use tools effectively. It's not just about any reward signal. You have to think carefully about what you're rewarding, how much reward, and crucially, how detailed that feedback is.
Right. And we
And
saw some really surprising results along the way.
definitely. Like that finding that just encouraging longer reasoning chains isn't always good and can even backfire, that's a big one.
Yeah, challenges common sense about.
And also, the clear benefits of dynamic reward scaling, letting the model learn gradually, and the real power of that fine-grained, detailed feedback for guiding the learning, those are huge.
It really feels like this kind of research is pushing LLMs forward, moving them away from just being text predictors towards being more, well, autonomous agents that can actually do things in the world.
Absolutely. And if we connect this back to you listening in, wanting to stay on top of the big AI advancements, this work is right there at the cutting edge. It shows that by getting smarter about how we provide feedback, how we design these incentives, we can unlock a whole lot more potential in these already powerful models.
So the paper title was Reward is All Tool Learning Needs. If that's even directionally true, it really makes you wonder, doesn't it? What does this imply for designing rewards for even more complex agent behaviors, like creativity or long-term planning?
Yeah, or maybe what other intuitive ideas about training AI might actually be less effective than we think, like that longer reasoning is a better idea.
It's definitely food for thought.
And maybe a final thought for you to chew on.
Oh.
How could these principles about clear goals, detailed feedback, maybe gradual difficulty, how could they apply in other areas where learning happens? Not just AI, but maybe education, professional training, even just learning a new skill yourself.
Thinking about how to give truly effective feedback for complex tasks.
It really underscores that understanding incentives, understanding how to guide learning through feedback is just fundamental, no matter who or what is doing the learning.